Welcome to the second part of our calculus class. We will start with the mean value theorem and may call it the MVT from now on. The mean value theorem relates the average rate of change and the instantaneous rate of change of a function. In more detail, consider a function x of t over an interval a to b so that the endpoints are a x of a and b x of b. Recall the average rate of change of the function x of t over the interval a to b is geometrically the slope of the secant line through the two endpoints. Recall also that the instantaneous rate of change of the function x of t at a point t1 between a and b is geometrically the slope of the tangent line at t1. Notice the average rate of change is only one number, but the instantaneous rate of change can take different values at different points within the interval. So how does the mean value theorem relate these two? Well, as you will see on our graph, there is a point at which the tangent is parallel, in other words, has the same slope as the secant line. Let us find such a point now. We can shift the secant line without changing its slope until it is tangent to our graph. And here it is, a point at which the tangent is parallel to the secant, and we will call this point C. So the following is the conclusion of the mean value theorem. There is some point C in between the endpoints A and B, such that the average rate of change from A to B is equal to the instantaneous rate of change at C. Or again, geometrically, there is some point C in between A and B, such that the slope of the secant line through the two endpoints is equal to the slope of the tangent line at C. Notice the MVT says that such a C is strictly in between the endpoints, but it does not say where exactly such a C is, or even how many such C's there are. In fact, there are two such C's in our example. We have only talked about the conclusion of the mean value theorem, but what about the hypothesis? In other words, when does it hold? To find out when the theorem holds, let us now explore when it fails.